Oh, actually that's completely not what I wanted. So 2 weeks wasted. But that was fun. Okay, so this is much more exciting because I know this stuff. So, this is 2/3 in, almost done. The big thing is that from this week going forward, this is where I can help you raise your grade. But beyond this week, it's going to be a bit late. And when I mean a bit late, it's like it's going to be hard to raise it because everything's going to be averaged at that point. And if everything before now is looking kind of solid, from here on we can raise you by a whole letter grade. However, from here, like after this week, because this week we have 2 worksheets due, we have a lab due. So after this, plus of course the quiz, that's a lot of points. And after that, we don't have that many options. Not options, I mean opportunities. We don't have as many worksheets and things. So if you want to do that, let me know. We start setting up meetings, emails, I don't care, of you asking me more and more questions, and we can say like, okay, here's where the weak spot is in your grades. That's where we're going to focus to help raise you up, okay? All right. So like I was saying, it's never too late, so just reach out and we'll get that sorted. Finally, some housekeeping. As I told you, there's 2 worksheets due this Sunday beyond the regular blah, blah. But the big thing is that you can do already the rate laws and orders stuff. If not, we're going to go through a quick review of it in the recitation guide. It'll hopefully make a bit of sense. And then, of course, after today's recitation and tomorrow's lecture, you should be able to do the half-life one. If you can't, or if it's not making a lot of sense, email me. Or, of course, there's Dr. Harwood and Dr. Towns who can help. But I would love to help you as well. Okay? Right. So, the big thing with this lab is figuring out the 5 main factors that affect a reaction. The reactivity of a substance. How reactive is it? Is it going to be a neutral thing? Is it a little bit unstable? The concentration of the reactants. Okay? As well, so when we think of like reactivity of substances, we're thinking of both the reactants in this. If I have a weak acid versus a strong acid, the strong acid is going to be a lot more reactive than my weak acid. When I think of the concentration of the reactants, I'm talking about the acid just as much as I'm talking about this metal. If that metal is a certain concentration and we change it, that's just as good as also changing the concentration of our HCl, our acetic acid, sulfuric acid, all those good things. Temperature of the system, adding in heat, giving energy to the system. Heat is energy. If I heat up something, I am packing it full of energy. That is going to make it go quicker. Finally, the contact surface area. It's a lot harder to break apart something that's a full piece. But if I break it apart beforehand, I've helped out the whole system. It doesn't have to break it into mini pieces and then dissolve those pieces. Those pieces are already broken up. So now the acid can just dissolve the tinier pieces. Next, the presence of a catalyst. Catalysts lower that activation energy. So when you're thinking of a sort of reaction-based curve, right? Where we have this, and you have your reactants, you have your hump, then you have your products. We have our activation energy between here and here. If I have a catalyst, I'm going to lower that distance, right? That's a good thing to do. So all these things to help make something move quicker. Okay, so things you're going to investigate in the lab. First, you're going to see what it's like we were saying, reactivity of a substance. If it's dirty versus if it's clean, is that going to change how it reacts with something? Then you're going to see the reactivity of different strengths of these different acids, right? I've got sulfuric and hydrochloric acid, 2 strong acids. Then I've got phosphoric and acetic acid, 2 weak acids. How's that going to change stuff? I change the type of metal. I want to see what kind of metal works best. I'm going to change the concentration of my acid. When it's less concentrated, is that going to change its reactivity? Probably. I'm also going to work here with different types of temperatures. If I add in heat, I am adding in more energy. I am then helping molecules move quicker, collide quicker, and if they do all those things quicker, the whole reaction moves quicker. And finally, we work with granular versus clean zinc, and of course the granular zinc is more broken up. That greater surface area doesn't mean that it's harder to break down, it means it's easier to break down, because now all sides of that are completely free. But if I have a big chunk of metal, it has to break off that metal and then break it into bigger pieces. If it's already broken into many pieces, it can now just start dissolving them easier. But if something's more compact together, it has more surface area within itself. It's more crystalline. And if it's more crystalline, it's harder to break apart. And then finally, you're going to look at peroxide and tap water with potato extract and see how that reaction was scored. Talking about something completely different. Some pictures I wanted to show you. So at the top, we took pictures, and you've also seen the video maybe, where we can see that there's HCl and sulfuric acid, got a lot of bubbles going on. That's pretty bubbly. That would, I would assume, mean the reaction is going pretty quickly. When I look at acetic acid and this phosphoric acid, those two things don't have as many bubbles. It's probably not moving as quickly. When I look here in the cold one, we got some bubbles going on, but here I've got a big bubble. I've also got a lot of this. I know this looks like a bubble, it's not. It's apparently the test tube, it's broken. And then in this one, I've got a lot of fuzzy bubbles here when there's a lot of heat. So we can see how the reaction is speeding up more quickly. Another thing would be using these pictures. Ooh.
So as you said, that one that is the fast, like room temperature is having a faster reaction than cold?
Yes,
Okay.
definitely. Yeah. And then we could pretend that all these are HCl, but I'm changing the concentration. So if I were to think of it like that, I would say something like this is that 2 molar, right? Because we got a lot of bubbles going on right here. And then I would say something like this is maybe 1.6 molar. Ooh, that's a weird 6 because this hand is hidden under here. And then I would say between these two, this one's got a bit more bubbles going on. So this one is probably like the 0.8 molar one. And then this one is like the 0.41, if we're thinking about it. Right? Because it would make sense that the more concentrated one would have a lot of bubbles, and then we just go down based on the number of bubbles. Yep. Everyone sees that? That makes a lot of sense. Great. Okay. Any questions on the lab? Anything that didn't make sense, sounded a bit funny, weren't happy with? We're happy with that one? Great. Okay, we're going to move on then to the recitation guide. My only gripe with it, obviously, is that this one doesn't allow us to see. So I'm hoping that I'm close enough. We're a bit closer now. Okay. So, first things first is we are working with a first order reaction. That's something that we always got to know. What kind of reaction order for the overall reaction is it? Next thing we're going to know, it says there's a rate constant of 3.72 times 10 to the negative 4 per second. That's another thing we got to recognize. It says calculate the half-life of this reaction in seconds. Okay, at the same temperature. Of course, we know that's important. Temperature changes the reaction rate. Okay, first things first is I need to know the kind of equation I'm going to use. When I think of half-lives, I think of a zero-order one, and that's the concentration of the reactant at the initial concentration divided by 2 times the reaction constant. Then if I think of something like a second order, this is where I now have 1 over K times that initial concentration. Finally, the one I've been looking for is a first order. And this is the one, sorry, these all equal to half-life. I've been just being silly. And then this one is the natural log of 2 divided by that rate constant. And that also equals a half. As we've said, we're working on a first order reaction. So I'm going to use this equation. Then it's giving me my rate constant. This is my K value. So all I've got to do is take T of a half equals the natural log of 2, which is 0.693, divided by that 3.72 times 10 to the negative 4 per second. And that in and of itself is going to equal 1,862.9 seconds, right? Everyone sees that?
What do you get 0.693?
0.693 is just if I plugged in the natural log of 2 in my calculator, it would equal 0.693.
Oh,
Yeah.
So you just plug it.
I just plugged it in. I just simplified it. Yeah. Should say this equals the natural log of 2 divided by our K value. Yeah. Okay. All right. Next. Now I've got the half-life of a first order reaction, and they've told me it's 12 minutes. What is the rate constant? And it wants it in seconds. So this means I'm going to have to take that 12 minutes, multiply it by 60 seconds per 1 minute. Cross out my minutes, and I get 720 seconds. That is going to equal my half-life, my t and a half. Next, again, it says it's a first order reaction. So this means I know that t and 1/2 equals that natural log of 2 divided by k, and I want to find k. So if I rearrange this, k equals that natural log of 2 divided by t over 1/2. So that means that if I want to make this equation, I'm just going to say my k equals the natural log of 2, 0.693, divided by 720 seconds. And that in and of itself equals 9.625 times 10 to the negative 4 per second. That is seconds in my denominator. Everyone sees that? Great. Okay, we're going to do something literally the same. It says in number 3, calculate the constant for first order decay. It's the same thing as the first order reaction of decomposition. We're just calling it decay. We're just getting fancy with our words. It says the half-life is in days. So again, the trick with this one is writing it all out. I'm not kidding. Best to just do this from the get-go, because if you write it all out, you don't miss any of the conversions. So what I mean by that is you have 2.356 days, and times that 24 hours divided by 1 day, times in an hour there's 60 minutes in 1 hour, and then as we know there's 60 seconds per 1 minute. Again, I know it sounds like a lot and it's like we could do in our heads, but I guarantee you, you always forget one of them. You either forget minutes per hour, seconds per minute, hours per day, and it just doesn't come out right. So this in and of itself is 203,558.4 seconds. Great. Now it's saying calculate the rate constant. So as we know up here, my rate constant is equal to the natural log of 2 divided by t1/2. So I know that k is going to equal that natural log of 2, 0.693 divided by 203,558.4 seconds. Which, as you guess, is a really small number. It's 3.404 times 10 to the negative 6 per second. That makes sense though for us because we're thinking the half-life is in days. So this thing takes a while to decay. Happy with that one? Good. All right, next one we're going to use a new equation. This is something that you're going to learn in lecture tomorrow. It's essentially how to do these decay ones when they've given you the beginning mass, when they've told you how long something has been decaying, and then they tell you its half-life. The equation you're going to use when you have first order kinetics is the concentration of A at time t equals the initial concentration or mass of the exponential to the negative rate constant times that t. So, like I said, they gave us t. It says how many of this is after 28 days. So t equals 28 days. Next, it says how much of t remains. So it's wanting to know A of t. So A of t is our x. We don't know. Then it says first order kinetics. So we know it's this equation. Has a half-life of 13.57. So we're going to use that to find our k. And it says our initial mass is that of 10.50 grams. Okay, to find k, what we're going to do is we're going to take the natural log of 2 and divide it by our half-life, 13.57 days. I'm going to keep it in days because my t is also in days. And since they're multiplied together, I want those to cancel out. So I'm going to keep them together. And that equals 0.051 per day. Great. Now I take all this and I just plug it in. So my A of t is my x value, so I don't know what it is, equals 10.50 grams, e to the negative 0.051 per day times 28 days. So these cancel, that's what I want to see. This equals 10.50 grams, e to the negative 1.43. If I take 10 grams times e to the negative 1.43, I'm going to get 2.51 grams. And that's how much will be left after 8 days. Does that make sense for everybody? We see that? Yeah? The biggest thing with these ones, again, knowing these equations. And they are Googleable, a weird way to say it, but they are. And you will find them out tomorrow in lecture.
What do you call T? T is 28.
Yeah, because we go up here and we say, how much remains after 28 days? So we know that this is what we want to find. This T is at 28 days.
Wait, how much? Oh, good, it's 28 days. I couldn't see it.
No, you're fine. I circled it. Maybe I. Yeah. So here's our 28 days. That's T. First order kinetics, so that this is the setup. So if it were second order, this would not look this way. It would be 1 over, and it would be times, or sorry, plus K times T. Sorry. You'll find out tomorrow. I'm not going to try and remember it off the top of my head, because luckily you all get to take notes on these, and you don't have to memorize them. Unlike, I think, 115 and 160, where they must be memorized. Or they're given. I can't remember.
You did this in 115, didn't you?
Yes.
Okay, I was about to say, this kind of seems familiar.
And yet, we wish we didn't have to. Okay. Next, what it's saying, what is the half-life of this first order decomposition? That's good to know. Of A to B based on the following data. Okay, so this is a new way to use that equation we just used. So, again, it's first order. So that means I'm using my A of T equals that initial concentration of A of e to the negative k times t. Now, what we're going to do is we're going to say this is our A of T. So here's our A of T, and here is our T. Our A initial is going to be when T equals 0, right? That's what that tiny 0 means. So this will be my A0. Now I'm doing this to find the K. Because remember, we want to find our half-life of first order. That is going to be T a half equals the natural log of 2 divided by K. So I need to find my K value. So A of T, 0.75 moles. That equals an initial of 2.0 moles. E to the negative K we're trying to find times 15 minutes. All right, I do all of that. I'm going to find that, find my own notes. I'm going to find that K in and of itself equals 0.065 per minute. Again, we know that because these minutes would have to cancel out. So it's per minute. Now, I just have to plug that back in to my half-life equation. T of a half equals the natural log of 2 divided by 0.065 per minute. And when I plug all of that in together, I get 10.66 minutes. And that's going to be my half-life. So that's the longest kind of question that you're going to get for something like this. So it's using this equation to find your K value to then plug it in to find your half-life. All right? That's going to be the longest one, where you have to have a data table as well. You see that? That looks good. Okay, the next one. So, as we remember, these are kind of hard when we look at them at first, but we've got to break it down a little bit. So I'm going to have us really think back to those half-life equations that we just wrote, right? So for 0, the T a half equals the concentration initially divided by 2 times K. For first, that T a half equals the natural log of 2 divided by K. And finally, that second, that's when that T a half equals 1 over K times that initial concentration. I see all of these. Now I get a fun thing to do. I look here at this first graph. I have the natural log of A of T. I have the natural log of the initial concentration. With that, when I look at these three now, the only one that has a natural log symbol in it is the first. And so I can just go match them up. This is for first. Next, now I look here. This has 1 over A initial, and in the vertical axis, it's 1 over A over T. When I look at these guys left, the only one that has 1 over A initial is the second one. And so then I just go, here we go, this one is second. Finally, to double check, again, My vertical axis is A over T. My A initial is as is. The only one that has A initial as is the one in the numerator, and that is 0. Everyone see that? That's pretty straightforward. Yeah? Awesome. Okay. Now, here's going to be one that we review a bit of rate orders and also rate laws. And this is going to help with that previous worksheet you could have done last week, and also for in case you haven't done it for the Sunday. So, based on the table below, determine the initial rate of disappearance of B if the concentration of A equals 0.3 and the concentration of B equals 0.2. First thing first, we look through here. I don't see anywhere where the concentration of A equals 0.3 or the concentration of B equals 0.2. So the initial rate of disappearance for that, I'm going to have to find through the rate law. To write a rate law, we not only need to know K to find that rate, but we also need to know the rate orders, the total order. So what I'm going to do is, I have the rate, that equals K, times the concentration of A to X, we got to find X, times the concentration of B, so I got to find Y. Okay, how do I find X and Y? Well, I've got to now refer to my data table. So what I'm going to do is, I'm going to look here, I'm going to look for a place, if I'm going to look for A, to find out what my X equals, I'm going to first compare where B is the same. So, when I'm looking at trials 1, 2, 3, 4, and 5, trials 2 and 5 are where B is different, or sorry, B is the same and A is different, and then 3 and 4 is where B is the same and A is different. So I'm going to do these two, and when I compare 0.2 and 0.4, if I take 0.2 times 2, I get 0.4. Next, if I look at the rates, 0.127 and then 0.5, to get from 0.127 to 0.5, I would have to multiply this by about 4. So, as you remember from last week, if I double the concentration and the rate quadruples, that means that this is a second order reaction, right? Because 4 divided by 2 is 2, and also this means that anytime the reaction is doubled, then the rate is squared, and vice versa. That makes sense? Everyone sees that? All right, next is B. So what I'm going to do with B now is I find somewhere where B is different and A is the same. So my options where A is the same is 2 and 4 and 3 and 5. So I'm just going to do 3 and 5. So I'm going to take this 0.3, this 0.6, and between these I would have to multiply 0.3 by 2 to get to 0.6. When I look at their corresponding rates, I see that 0.25 times 2 would get me 0.51. And so that means that if the reaction concentration is doubled, and therefore the rate doubles, that then my Y is going to equal a first order reaction. So that means they're directly related to each other. So now I know my whole entire rate law. And now I can plug in stuff to find my K. So I know that my rate equals the K of A squared times the concentration of B, where it's raised to the single power, but we don't have to write that if we don't want. Now, I'm just going to use this first line to find my K value. My rate is equal to 0.027 moles per second. That equals my K value. My A is 0.1 squared, and my B is 0.5. Now, I take 0.027 moles per second divided by 0.005 moles cubed, and that's going to equal my K value. Because again, this sign equals molarity, and so I'm going to get, when I do all that, my K equals 5.4 per meter squared per second. Awesome. Okay. Yeah? Next thing I'm gonna do now is I just gotta plug this in to my new equation now. Because I know the rate equals 5.4 meters per squared per second of the concentration of A squared times the concentration of B. So now to find my rate, I just have to plug these in. That rate is going to equal 5.4 meters per square per second of 0.3 squared times 0.2. And that is going to equal 0.097 meters per second. And we know that because if I were to do this, this is meters cubed times meters per minus 2 times s minus 2. So if you take 3 minus 2, that's 1. And then seconds is negative 1. So it's meters per second. Everyone sees that? This is the perfect kind of review for rate law and rate order stuff. That makes sense to everybody? Yeah? Seeing some thinking going on.
Is it meters?
No, it's molar. It could be meters, as long as there's an M there.
Okay. I think I did.
No, it's okay. It's just that this sign, these two brackets this way, actually is just implying for that moles per liter. So here we just kept it as is.
Okay.
Mm-hmm. Everyone happy? Awesome. Okay, the next one, way more fun. It's a picture. Okay, we're assuming first order. We're going to see why in a minute. Basically, we're saying yellow at t equals 0 seconds is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, wait, I counted this wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16. The yellow at t equals 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8. If I take 8 divided by 16, that equals 1/2. So then we know that the half-life of this reaction is 10 seconds. We also know, based on how it decreased linearly, that again the concentration doubled, and then we know that it went down by 1/2 linearly. That is going to inline with, where'd that go? With our graph here, right? It's a linear descent. So for us, we know that this is also first order. That's great. Now it says calculate the rate constant. Well, since we know it's first order, I know that t1/2 equals the natural log of 2 divided by k, and therefore k equals the natural log of 2 divided by 10 seconds, and that means it equals 0.0693 per second. Right? That was easy. Okay. Next, it finally says, how many yellow spheres will there be at t equals 40 seconds? Again, this is first order, so that means I have my concentration of A at t, which is what I'm finding, my initial concentration of A, e to the negative k times t. T is 40 seconds. My k is 0.0693 per second, and my A initial is 16. So this equals 16 e to the negative 0.0693 per second times 40 seconds. So that equals 16 of e to, just keep looking here, to the negative 2.722. And then that means that we get A of t equals 100. So there will be one yellow sphere at t equals 40. The other way to calculate that, of course, half-life is at half-life is at t equals 10 seconds. The half of 8 is now 4, 20 seconds. Half of 4 at 30 seconds would equal 2. Half of 2 is 1, and that will be at 40 seconds. It's a linear descent. That's nice because these are nice and big numbers. Obviously, I don't recommend using that kind of style, but with this one, it's a nice mental check. It makes sense to us. If it's not a beautiful round number like 16 that has a nice half, I definitely recommend just using this equation. It'll get you the right answer every time, regardless of your math skill, as we've proved.
With that equation, we can use like grams or the concentration.
Doesn't matter.
Okay.
As long as what you're finding is the same. Definitely.
Wait, how do we find homocysteine?
Oh, that's what we found here. This one. So we found T hat was 10 seconds,
Yeah.
so then we found it there. It's all connected, it's just on a different page. This is part C. Okay, last question. Whew, okay. Thermal decomposition of a molecule X follows first order kinetics. A plot of the natural log of the concentration of X versus time has a slope of -4 times 10 to the -3 per second. What is the rate constant and the half-life for the reaction? Again, it says first order kinetics. Now, when we think of first order kinetics, we then want to think of this graph. In this graph, it says the slope of the line is -4 times 10 to the -3 per second. But we see that the slope equals the -k. And so, since it says that the slope equals -4, we know that the slope is -k, which equals -4.00 times 10 to the -3 per second. And I want k, which means I divide all of this by -1. So k equals 4.00 times 10 to the -3 per second. Okay, there's my rate constant that it was asking for. Fantastic. Then it wants the half-life. You and I know that the t of a half equals the natural log of 2 divided by that k value. So this equals the natural log of 2 divided by 4 times 10 to the -3 per second. And that equals 173.25 seconds. Ta-da!
Wait, why did you equal it to the -k?
Because that's what we got from this graph. Right? It says it's first order. In first order, we see that the slope equals the -k value. And so here in the equation, in our question, it says this plot, which is the plot we just saw, has a slope of -4 times 10 to the -3. So then we just took the slope from that same plot is the -k. So I divide all of that by -1 to get my k value. Yeah. Any other questions on this one? No? Happy? Pretty happy? Feeling confident about those 2 worksheets for Sunday?
Half-life for sure.
But still.
Yeah, the other one, yeah.
Definitely review this one. And then last week, I think I have last week's. Let's see, this one, where we did these. This is a good one too.
So will our quiz be just kinetics in this week?
Yeah, lots of kinetics.
Okay, cool.
Great. It will be asking you things like in your pre-lab about the factors that affect it. So don't be swayed. Make sure you know what factors do not affect your reaction rate and which ones do. It's going to ask you something like this. Find the rate law for sure. Just remember the rate law is always the rate equals K of the concentration of the reactants. And then remember to compare your rates to your concentrations. And if they increase by the same number, multiplied by 2, then that means it's first order. And if they increase by 2 squared, then that means that, aka quadruple, then that means that it's second order.
So, to find what A concentration, you would look in the first, you look at the rates, right?
Look at the rates. We're finding X, not the concentration of it. We're just going to
Oh,
find
yeah, the X, yeah.
Yeah, those ones.
You did that by, so in the A column, 0.250, 0.250, and then you went over to the rate and saw it multiplied by 2. And you do the same for B.
And also, what people don't know is you could go the other way. You could say 0.25 divided by 0.5, that gives you 1/2. And then if you did it over here, 0.4 divided by 0.79, you also get about 1/2. As long as they're the same number, that's all you care about. The only time I'd be careful is if it, when we divide and get small numbers, is it almost looks like 0. But with zero order, you just have to remember that if this doubles and the rate remains the same, so like here, we can see in this one, A, the concentration doubled, but that rate stayed the same. And so that's why in this rate law, A is not listed, because it's to the 0 power. Yeah. So that's why I said A to the 0. Yeah. Does that ring bells a little bit? A little bit. Good. Okay. Who's got questions on the pre-lab about rate stuff? You go through that, see if we can answer some of those.
I have questions about the graph.
Oh, that one this one I just drew.
Yes, that one.
Okay. Let me.
I just don't know which one's the catalyst.
So, as we just drew here, this is that. I was hoping that would answer that question. Let me blank. Okay. So, this is our reaction coordinates. So we say this is just where the reaction is going, and this is energy. So, we start here. These are always going to be our reactants. This is where we start. Wherever you see it just staying like this, that's our reactants. Then, you're always going to see it pop up, and then come down. Now, in my defense, this is an exothermic one. Another way this could go is you have the reactants and the products up here. This is an endothermic graph. We're going to focus on an exothermic because that's the one on your pre-lab, but just know in your lab, you actually have an endothermic one. Okay, so just keeping that. So this is the products down here. Great. Now, this right here, this is your activation energy. Right? Everyone knows that? That seems pretty familiar. This whole thing is the energy of the total reaction. What I mean by that is, it's the activation energy, but as well, it's the energy that's released in the system. So it's the total energy of this reaction. And this is the energy released. So anything here, this is your starting energy, right? We start with this much, and then we end here, so this must be how much energy we lost. This energy to here is how much energy we need to get this reaction going, so we call it the activation energy.
Is the activation usually the catalyst?
It is, but it's not the catalyst in the direct term.
Okay.
So what we mean by that is if I had a catalyst, that would make that hump smaller. So the activation energy is now smaller. So the catalyst changes C on that graph because it makes C smaller. Does that make sense? So to answer your question in short, it is C in that answer, but the reason for that being is it makes C smaller. Everybody see that? So the answer in the multiple choice is C. It is changing that part of the graph, but it's because it's making it smaller. So if you read the question, it's not asking which one of these variables is the catalyst. It's actually which one of the variables would the catalyst affect, and that is the activation energy. So it's taking the activation energy and lowering it.
So that's not a catalyst. Okay, something. Okay, now I'm
Yeah.
incorrect.
Yeah, it's like, that's why it's not asking you which one's the catalyst. It's asking which one does the catalyst affect. And the catalyst is the one that basically lowers this activation energy. So, if you ever see it in like a written equation, let's do zinc, let's do Cl, this becomes zinc, chloride, hydrogen gas, plus CuSO4. which one is the catalyst in this written equation? It's one of your pre-lab questions.
A it is.
It's not directly, but it's asking you to define a catalyst.
It's not,
Not HCl.
so,
It's okay. So a catalyst is something that speeds up the reaction.
Oh, it doesn't change.
But it doesn't
Yeah.
change. So it's got to be the
Okay.
same on the other end. So in your thing it says is used up or something like that. I can't remember. But it's not that it's used up. It literally just lowers the activation energy. That's all it does.
and the question what you're saying, which of the following changes can increase the rate? You said it was all of them?
Yes, I think. Let me double check.
So replacing large pieces of metal with metal does.
Yeah, definitely. And then replacing the HCl with a weak acid. Now wait a minute. What that question says? There's something about increase. So the one that doesn't increase it is this one. Because you're going from a strong acid to a weak acid.
Yeah.
Yeah. Oh no, this one yes, that one no.
So which one that wouldn't affect it with the molar mass, right? That one I did not understand. What was the molar mass of the reactive matter?
Oh, which the following factors does not. So the molar mass does not affect it, right? Because we're talking about when we look at the relationship here, the molar mass is not going to change the concentration of these because I'm always looking at the concentration of zinc, T versus the concentration of zinc at time 0 of e to the negative k times t. It's always the concentration. The molar mass is not the starting mass, it's just a mass. Does that make sense? So like the one that we did here where it was 10.5 grams, that's 10.5 grams, but that's not the molar mass. That's just a mass. Does that make sense? So the molar mass is an arbitrary number that you could use to find the moles to find this concentration, but that is always going to stay the same, so you can't change it. Does that make sense? So it wouldn't matter if something is intrinsically heavier. What would matter is how much of it is there. Is there 10.5 grams? Is there 0.5 molar? That's what we care about. We don't care its molar mass. It doesn't change the outcome directly. Does that make sense?
Yes.
Yeah. Yeah. That comes from the periodic table, so that means it doesn't change.
So what changes is temp, catalyst, concentration, and maybe something else? I know
Reactivity of the substances. So what it means by that is things like that one where I said replacing HCl with the phosphoric acid.
Yeah.
So with that, by changing the phosphoric acid to phosphoric acid, you change the reactivity of the substances at play. Because now you've gone from a strong acid to a weak acid. So that would decrease how reactive something is.
Wait, wouldn't humidity also?
Humidity has no effect.
No, that's not temperature. I'm sorry.
I get what you're thinking though, you're right. When it's humid, it's hot, but it's the heat itself, the temperature that's making it humid. The humidity is a side effect, not a direct effect. Does that make sense? So I get why you said humidity. The problem with humidity is it's a side effect to what's actually happening, which is temperature change.
What, I thought you said a catalyst could direct the reaction along the higher or lower. Or is it always higher?
No. This is the one. It lowers it, so along the lower one.
Yeah, but in this question, is that a catalyst would direct the reaction along a blank higher or lower?
Lower, right?
Energy path.
Isn't this a lower energy?
So isn't the top one a higher one?
Yeah, the top one is higher, but the catalyst makes it lower. This is our catalyst path.
Oh, okay.
So the reason why we want it is if you think about it, you have to bike up a hill. I'd rather bike up this hill than this hill. So as a reaction, it's the same. And when the catalyst does this, that helps speed it up. Less of a hill to climb. So that's why the catalyst makes it speed up. We're going over a tinier hill. So it will always make you go over a lower one. For the pure fact of it's easier. We like easy. Reactions like it, I like it. Yeah.
So the smaller, you said in the lecture, like the smaller area there, the smaller circumference, so it's going to be a faster
Mhm.
reaction.
Just because less energy needs to go into breaking it apart because it's already broken apart. It's like, think about it, if you eat stuff, like on a stomach, like say you're really hungry, you chew stuff really quickly, don't really chew it, you get an upset stomach. That's because your stomach is actually doing a lot of effort to break down the food that's already not broken down. You chew more, you get less of an upset stomach for the pure fact that you've already given it broken down enough to where your body doesn't have to use more energy to break it up. That's why they tell you if you're out and starving in the middle of nowhere and you find some food, definitely chew it as much as you can because that gives your body less work to digest it. That's just the idea.
So the smaller the surface area, the faster the
But then this makes no sense because the video we watched in the lab, there is a little bunch of small beads
Mm-hmm.
and a big rock. And that rock starts to react with the rock way faster. Are we looking at how fast it breaks it down or the reaction of it?
Wait, it's the surface area.
The surface area.
The larger surface area would make it
Slower.
Yeah, I don't understand the video.
Well, think about it now. If I break things into little pieces, now I have a lot more surface area. Right?
Yeah.
Right. If we think about a cube, if I break it into tinier cubes, now I have more sides of the cube, so there's more surface. You know? Am I
Oh,
going-
you're talking about the size. Oh, I'm thinking of the size.
No, yeah. I was like, I'm talking about surface area.
Okay, I get it now. It's,
I was like, I feel like I am missing a link. What's the link?
okay, that makes so much sense. It's only like that big rock is not as much as 1%.
Yeah.
I didn't understand what was happening in the potato extract. That was the only question I had.
So you have potato extract in water and you're acting it with peroxide.
Yeah.
And what's confusing? What's giving us the trouble?
Well, it says what component in the potato extract may cause the H2O2 decomposition, right?
So when we think about potatoes, what's a big thing? Yeah, starch. Don't worry about thinking about it too much.
You say cite the source stuff? Well,
I was gonna say, you can't cite me. I'm not a source.
yeah, no.
I wouldn't cite me for anything. How's this going? Yay!
We did it all night.
All right, so then one more question I just have.
Yeah.
It says, do you notice any changes in for the search area one?
Yeah.
Or search country? Yeah, no, it says area.
Mm-hmm.
There's no, I said, did you notice any change in kind of rate of reaction when both two people are reacting?
The surface area, you should see, oh, yes.
I don't understand the question, so I said no.
Should we do it? You should notice a change in the rate of reaction.
Once they've begun?
Yeah. So look here. So notice this one's bubbling and then this one bubbles as well. And then if you go towards the end, see how this one's getting fast? Starts bubbling over, and then this one's also pretty quick. So you can see that one's kind of fizzled up. So this one has reacted a lot quicker than this one. Yeah.
That's what it means for that.
Yeah, just like observation stuff. Doesn't have to be your most elegant work. Just a quick, what's going on thing.